Hello, my name is Anthony Mwanthi from the University of Nairobi, and my presentation is on land atmosphere coupling processes in CMIP6 models. Some of the previous research that motivates this study is listed here that indicates that models that better represent the land atmosphere interactions also show better skill in overall atmospheric processes. And there's also interest in utilizing soil moisture to improve subseasonal forecasting. And we note that during extended dry periods, we also have temperatures tending to rise due to soil moisture feedbacks. And in future climates, temperature extremes are expected to be amplified due to feedback mechanisms of drying trends of soil moisture. Our area of interest is over Africa, as highlighted on the figure on the left. And this is leaf area index plotted to indicate, using vegetation to indicate the different climate regimes over Africa. We have 6 sub-regions of interest. And for this presentation, we'll present highlights for Central Africa, East Africa, and the Sahel. On the right, this figure is from Miralles et al. 2014, and based on the study for the major heat waves over Europe in 2003 and 2010, even with the relevant synoptic conditions, this study noted that the decline in soil moisture introduced feedback that actually enhanced the heat waves to such magnitudes that were recorded. For the data, we utilize soil moisture, latent heat flux, precipitation, and evapotranspiration, as well as leaf area index. For the models, the data was already available in Jasmine. For ERA 5, we sourced this from the Copernicus climate data store, while for the leaf area index, this was sourced from the Global Inventory Modeling and Mapping Studies archive. In terms of the metrics that we were interested in, we were interested to represent the land atmosphere interactions, and this was done following the Mayor 2011. So this process was represented in 2 segments, the terrestrial and the atmospheric segment. And the indices were a product of the correlation with the standard deviation for the variables of interest. Starting with the annual cycles over the different sub-regions of Africa. On the top panel, this is Central Africa, while the bottom panel is East Africa. The reference data here is ERA 5, which is shown by the black line for P minus E, as well as soil moisture, while for leaf area index, the reference is the maroon line, which is GIMS. So we note that during the peak of the variable P minus E, that is when we have major model differences for Central Africa, and this is true for all other regions actually. And here we note that for regions, for models that have less or small magnitudes of P minus E, they also tend to have small magnitudes of soil moisture. And here we note for Central Africa, despite the differences in magnitudes of P minus C and also soil moisture, the annual cycle is consistent with observations, and especially for leaf area index, we note the peak is in April, not in November, when we have the highest amounts of rainfall. Over East Africa, we note that some models give an early peak of the first of the short rains in October rather than November. But surprisingly, that is not transferred to either soil moisture or leaf area index, because for the first season, that is the short rains, all models show the peak in soil moisture in November, while leaf area index peaks in with the 1 month lag for East Africa. In the Sahel, we note that some models here we expect the peak of the P-C will be during the Northern Hemisphere summer, and we note that some models do not actually indicate this. It's P-C is just around the 0 line, and these models also have the least soil moisture. And we note that although a model here, UKESM, has the least soil moisture, it has the highest leaf area index that and that may not be very consistent with what is expected. But for sub-regions for Africa, we noted that the UKESM has the highest leaf area index and it shows little seasonality, while GIS E21G shows the least leaf area index. Now, the next item we considered was to map out the different soil moisture regimes of Africa, and this we present for the different regions based on Era 5. In Central Africa, this is a wet regime whereby there is abundant soil moisture, but soil moisture does not drive the variability of latent heat flux. That means the control of latent heat may be due to other factors such as net radiation. In other areas, such as the Sahel, during March, April, May, this is a wet regime because there's little soil moisture to drive variability of latent heat flux. While in other areas which are of interest in land-atmosphere interactions, like over East Africa, this is a transitional area, and this is where we have typical good relationships between soil moisture and latent heat flux, and such areas are of interest to look at how the models are able to map out the three regimes. So we present here the regime of Central Africa, and on the bottom panels shows how models simulate this for the March, April, May season. We see the top panel models are fairly able to simulate this well, while in the bottom, we have some 3 exceptions. The MIROC and ESM5 are not able to show there's no relationship in this region between soil moisture and latent heat flux, while the GFDL actually shows an inverse relationship. For the transitional zone of East Africa, here we see that the models are capturing this relationship. And so we expected that the models will also be able to represent this, the atmosphere interaction processes as forced by the land surface. Now, looking at the metrics that we were interested in, this is the terrestrial segment of the land atmosphere interaction for the 4 seasons based on Era 5. We show that during the JJA, the coupling is strong over the Sahel and parts of Central Africa, as well as East Africa and Southern. The Central Africa pattern is consistent with the annual cycle, because during this time, it's only when we have negative P-C and soil moisture is minimum. For the other seasons, we see there's strong land atmosphere interactions based on the terrestrial component of parts of East Africa and Southern Africa, and also south of the Sahel. Based on the atmospheric coupling index, we see similar results that this relationship odds during JJA for the regions in the Sahel, roughly also Central Africa, but for the other seasons, we see these good signals of East Africa Southern Africa and parts of south of the Sahel, especially during March, April, May. And we looked at the standard deviation of soil moisture and latent heat, and we noted that the relationship actually is driven by the variability of these two variables. So it was important to consider the standard deviation in the computation of the index rather than relying on the correlations alone. Looking at how the models are able to capture the terrestrial coupling index, the general observation is that for most models, they overestimate this strength, especially over Eastern Africa as well as Southern Africa. Models also tend to differ on the representation of this pattern, especially south of the Sahel. And also we note GIS as overall the weakest coupling index as compared to ERA 5, which is highlighted at the center. Considering the atmospheric coupling index, this is the result from the models. And based on ERA 5 as our reference, we note that also the models tend to overestimate this strength, especially over Southern Africa. And for some models, the intensity is very strong towards the south, while in the observation, the strength is towards the northern boundary of Southern Africa. This is for March, April, May. We also note model weaknesses, especially in the region south of the Sahel. This is not well captured for majority of the models, especially GIS, ANGM, UKSM, and also CAN ESM5. One of the variables of interest that drive or control the balance or the variability between the lower boundary moisture and energy fluxes is vegetation. And here we show that GIS has a typical underestimation of vegetation throughout Africa. And this may be one of the contributing factors to the biases that we noted in this model. For the UKSM, we noted that this model had nearly an invariant annual cycle of leaf area index, and it overestimated vegetation throughout Africa. But we see ANGM as the least biases in terms of representation of vegetation over Africa. Another aspect of interest was to look at whether we can take this result forward and utilize soil moisture to support sub-seasonal or seasonal prediction. And here we present soil moisture memory computed based on effort in time. And in summary, we note that soil moisture memory is important in regions where the rains are withdrawing. So in those areas, soil moisture can provide predictability even up to 40 days for some areas. And this is true for southern areas in Malawi, northern Mozambique, and Namibia, and also during March, April, May, and also south of Sahel during the SON season, as well as southern Central Africa. So in summary, we note that although Central Africa is a major region of moisture recycling, soil moisture is not an important forcing for the land surface fluxes. The GIS model consistently underestimated leaf area index, while the UKSM showed the highest magnitudes, and there was no discernible seasonality for this model. And we note in terms of the matrices, the soil moisture regimes together with the TCI and LCI, this characterization is actually useful for classifying how the models are able to capture the region-specific interactions of Africa. This could be a good metric to assess models. And how we noted is that most of the models studied in this presentation show an overestimation of this land atmosphere interactions over East and Southern Africa. And lastly, we note that there is potential to enhance subseasonal prediction over certain areas of Africa using soil moisture. Thank you very much.